I still have a lot to talk about, please. So I really tried to stop in time, but I still have loads and loads of slides, so please give me the chance to start. Welcome back. I want to spend a little bit of time of showing you how this A-star algorithm works in this specific search problem of Romania. And again, to remind you, the task was that you need to be in Bucharest, and the question is, from Arad, how to get there with the lowest cost in terms of time. And the distance is basically here given between the individual cities that you can get to. So from Arad to Sibiu, it takes 140 kilometers or minutes or whatever the time is. But we also have, and that is our heuristic H, the beeline distance or the shortest line distance. So that's these numbers. So we know that if we would go without any detour from Arad to Bucharest, it would be 366. And of course, as it's the shortest line, it is the shortest line, so there is no overestimation at all possible for H. And you also see it, if you look at one of the distances, would be 140 plus 99 plus 211, then we are already far beyond 400. That is a lot more than the 366 that we have in our straight line. And this holds for all the distances we have in our graph. And now the question is, how do we find our way from Arad to Bucharest that is optimal? And A-star is an algorithm that allows you to calculate the optimal path between these nodes. Remember that last time we did the greedy best first search, we found this solution, Sibiu, Fagaras, and then Bucharest. And I claimed that it wasn't optimal. Yeah, and now if you do the calculation with A-star, you should find the optimal solution to this. So how do we do that? We start in Arad, f of Arad. Is g of Arad plus h of Arad, and that is, what is it? 0 plus 366 is 366. Okay. So we have that in our fringe, and we know the value f for this. So if we have now Arad, we can look at all the children it has, and that would be Zerind, what was it, Sibiu, and the one I shouldn't try to pronounce, Timisoara or something like this. And now we have to calculate the f value for these things. So f of z is, and again, g of z plus h of z. So it's very, very simple. So what is the g value for Zerind? Anybody? 75 plus the h value is 374 is 944. Yeah. What is the f value for S? Yeah. So let's do it. Its g value is 140 plus 253 is 393, and the last one is f of t is 118 plus 329 or something like this. Yeah? Okay, so now we choose the one to explore first. We put all those things in our fringe, and we choose the one to explore first, and that's the one with the smallest value f value, and that is this one. Yeah? So now we're here. Yeah? So now let's look at the possible successors for CBU, and that would be going back to Arad, going to O, what is it? Oradeer, Fagaras, and R. And let's calculate, not Aras again, but let's do the Fagaras one. So we obviously would have to calculate all of them, but we do that later. Or I let you do that as homework. So what is the G value for F? It's the only thing which can go wrong in the exam, that you get me the wrong G value. So what is G for F? G of F. I hear the right number here. Anybody in the back with the right number? 99. That is one of the typical mistakes. The entire distance between the starting point and the node itself. Yeah, you're back? Exactly. So that is, yeah, you have to combine all the paths to the node. So it is the 99 that you mentioned, but it's also the 140 that you have to take into account for G. Yeah? It's always the distance from the starting point. So now we have 239 plus the distance in H, which is 176. And that is 51,451, and so forth. And now if you calculate A, O, and R as well, you will see that we don't get automatically down F and then to B, but that we take the way down here, which turns out to be the shorter one. Yeah? I don't want to lose more time on this, but this is the way just to go forward. Just write down for all the possible nodes that you could go. You write down the G value, which is the distance from the root to the node itself, and you add the heuristic value. And then you only have to make sure that your heuristic value, the B-line distance, is never an overestimation, and then you know that you have a complete algorithm. Is that clear? Yeah?
If we found out that our release group would be actually longer than targets, A star would backtrack.
Yes, A star always takes the one with the smallest amount here.
Okay, so it will backtrack to Fagaras.
It will backtrack to Fagaras. It is a best first algorithm, so it looks for the best solution but it's not greedy anymore. That's the difference. It's not greedy, so it doesn't take the shortest distance to Bucharest, but it also takes into account that in order to get to F, you need to travel already quite a long time. So in that sense, it's more efficient to go this road. That's all it does. Okay? And this A star algorithm is sort of one of the classics of the AI literature. Has the nice property that it is complete, so it always finds the shortest path. It's optimal in that sense as well. Unfortunately, you need to store all the nodes, but that still is okay, because you don't have to store the entire tree. So in a way, we do a depth first search. But the complexity, of course, is exponential with the path lengths that you need to travel to your goal. So, third part, more on the adversarial part. And we obviously spent a lot of time on that. So here's just some little leftovers that I want to talk about. Remember we had the very simple one where you could explore the whole game state until you found the end of a game, and then you could evaluate whether you won or whether you lost as max player. And you could optimize that by the min-max algorithm, where you would just calculate the minimum value that min could choose, and you would combine that with all the, you would take the maximum as max player of all these minimum values. And we looked into the point where you could sort of where you had to stop the search earlier because it was so inefficient. So we needed to assign estimations, again, our heuristic values to each of those nodes at the cutoff level. And we had some ways of doing this more efficiently with alpha-beta pruning. And in principle, these are the main things about the adversarial search. Yes, you have a point?
I still have one note on the map of remaining version about the sum of the cost from Arad to Bucharest passing through Faradas is higher than passing through Rimnicu.
Yes.
But still we say that's the optimal solution.
No. This is the optimal solution. Arad, Sibiu, Rimnicu, Vitesna, Bucharest. That's the optimal solution. So that's exactly where the greedy one goes wrong.
Right.
And if you do this calculation, it takes too long now. I leave that as homework for you. But if you do this calculation properly, you would find that the Rimnicu value is smaller than this 415. And then you would go in the next step, you would go down closer back. Yeah? Okay, good. Thanks for asking. I think it was a bit too fast, maybe. So let's see. One of the assumptions we had is that we only have 2 players in our game so far. And one could say, okay, maybe that doesn't work for 3 players, but it's in principle is relatively simple to extend. So now you wouldn't have a min value and a max value, which you can basically represent as a single value. But you also want to have a 3rd player, so your min-max values become vectors. Depending on whether you play with together with 2 players or each of you want to win, you might have different strategies to sort of assign new values to your, so each of the players would then correspond to one of the positions in the vector, and in principle you can apply the same algorithm depending on the moves, who's on the move, and what is the result of a move in order for your own gain or lose state that you want to record and that you want to build your strategy on. So this is all I wanted to say. So there is not this restriction to 2 people is more to keep it simple in the experiment and not so much a restriction of the principle. And the same holds for games with chance. And I said that Schnapsen is a game of imperfect information because we don't know where the cards are, but it's not a game with chance. So in a way, of course, there is an element of chance when the cards are distributed. But from the moment that the game starts, the game engine has assigned values to all the cards, where they are, in which position in the pile, on which hand they are. So at that moment, when we start our Schnapsen game, there is no uncertainty, there is no chance, no element of chance anymore. It's a deterministic game where everything is known and every state is statically derivable. Yeah? But there are games with chance in which you can still apply the strategy and where you can combine the information that you have about the uncertainty with the prediction of how good your game is going to be played by you and your opponent. So let's look at backgammon, for example. I don't know, who of you know backgammon? Yay, that's good news. So you probably know it better than me, so forgive me if I explain this the wrong way. But the idea is that you have a white player and a black player, and you have to move your stones from your own home to the opposite home. And you do that by moving first this direction, and then up, and then this direction as a white player, and as a black player, you do it the other way around. Or probably I explained it the wrong way around, so I think we have, in this situation, we have white move in this direction, so it has already quite some stones in her own field, and black has to move the other direction. Because the example shows here that we have you throw a dice, and every move you throw 2 dice, and then you can move according to the number of the dices to a new position. So here is, for example, a 6 and a 5 dice, and you can move from position 5 by moving to this direction as a white player with 1, 2, 3, 4, 5, 6. With this 6, you can move to the 11. Yeah? So, I'm not sure why you can move to the 10. Hmm? Oh, and a single one you can take. Oh, okay, good. Yeah, so here my not knowing backgammon shows. Okay, so yes, so if you go from 5 with the 5 to the 10, you can break the other, the black one. So that's a valid move. 5 to 10 is a valid move. 5 to 11 is a valid move. But also 19 to 24. So if you continue counting, you can move those stones somehow. And I think this should be more or less all you can do with the moves. Yeah. So there is a number of transitions. Of course, again, we got the same paradigm as we had before. You start out with a certain position, and then you throw the dice with a certain uncertainty, and this is the element of chance that we have here. You throw your dice, and when you get to one of the states, we're in the deterministic position again. So then we know exactly what are the possible moves you can make. And then basically you can combine the idea of your min-max search with throwing the dice and the probability of a certain state being thrown by the dice. And that is then combined into your terminal values, or the terminal values, of course, are determined by the end of the game, but the probability of you winning the game by doing this move is then a combination of this backtracking of the combination of the estimation of the probability of this move being happening and the probability of and the possible moves that you make. And basically this translates into the same algorithm, but now with a component of chance included. So you take the expected min-max value and you take the element of the probability of reaching a new state. So it's just in the combination of your construction of the values when you propagate the values from the node, the leaves to the root, that you take the chance into account. And that's in principle the only difference that you have when you apply such a game algorithm like min-max to a game now with an element of chance. And of course, the chance that you have a strategy that tells you whether you are always going to win or not is getting very small, but it still can give you an indication of which move will be better by combining the expected outcome of the game and the element of chance. So this leaves me 20 minutes to talk about rational agents, and this is basically how we used to start this lecture, and also how the book and the readers start. So after 4 lectures, we finally have the introduction to intelligent systems and to rational agents. And as I explained before, I left that out in the beginning because of the interest of getting you to the technical part as quickly as possible, so that you can now start, or could already start, with the programming and getting used to the game engine and understanding how the basics of this method work. But now it's still time, I think, a good moment also to go back and to reflect on what is it we are doing in the first place? Why are we here? And what is AI? What is intelligent agent? What is an intelligent system in that sense, or how do we mean that? And to me, the intelligent systems field is a subfield of AI, which is really about the building, explicitly it's the engineering part of AI, which is really about the building of artificial agents. So there's also other ways of looking at AI. So the cognitive AI, which is not so much about building the systems in the first place, but understanding intelligence more, and so forth. But here we really focus on the building, and that's why I also want you to have sort of the hands-on experience very early, that you understand, okay, if I implement my algorithm, my agent in this way, it will take too long to get an answer, so I have to do it differently. And this kind of experience, I think, is best made when you do the hands-on experiments. Okay, now I've hidden the question of an intelligent artificial agent. And there the definition is that a rational agent is an agent that chooses between actions, and it chooses the one that maximizes the expected value of its performance according to some kind of perception that it can make and knowledge about the environment that it has. And according to this sort of understanding of the world, it tries to maximize some expected value of outcome. So I try to explain that in a little bit more detail later. First, let me talk about agents, then the notion of rationality, and then an important question is that intelligent agents also need to take care of the environment they operate in. And that's not so much relevant for Schnapsen, because it's a very simple, it's a very well understood and controlled environment. That's one of the properties of these games. But it's still very important if you want to extend this to self-driving cars or intelligent search engines and so forth. So the notion of an agent is really something extremely simple. And it is something that has some kind of actuators. It can take some action, and that can be sending emails, that can be moving, that can be switching on a heating. And it does that on the basis of some kind of perception. And on the basis of these perceptions that come from outside, it takes some actions. So it's a combination of sensing information and with the actuators do some action, take some action. And in that sense, an artificial agent is already there. So I'm not sure whether it's this thing or the heating system. So there's one thing you do, you measure how warm is it in this room, and you have a sensor that measures this temperature. You understand this, what is understanding, but you have an actuator, and that is increasing the heat or decreasing the heat, and that is basically already an artificial agent. And then the question starts of where is the moment where this agent really becomes an intelligent agent or a rational agent. And you should be able to make the distinction, or you should make the distinction between an agent as a physical thing, so the thing on the board, so the agent program runs on some kind of physical architecture, but there is of course the sort of the concept and the function of what this thing is supposed to do. And the agent function maps the perception to some action, and that's where most of our algorithmic work here is relevant for. So we think of what is it we know of the world, what is it we can sense and so forth, or what are the cards we have, what is our state representation, and then we have some algorithms, we map it to actions, but we don't really care about the actions. You should then translate this agent function into a computer program that you implement, and basically then you run it on some kind of physical architecture. And the Bachelor AI student, we do that a little bit in the field trip, that we really look at some very, very simple agent that takes some information from the outside and takes an action based on some representation of the world. And then in principle, this is very often very simple. Now for the rationality, or what I would call an intelligent agent, is one that has an explicit notion of performing well with respect to some measurable criteria. So in that way, you could again call your heating agent rational and minimal rationality, because it has one objective, and that is to keep the temperature on the right level. But of course, in more complex environments, this also becomes a more complex task. So what the intelligence depends then on is on what is the performance measure. So what is it that you want your agent to achieve, and what kind of actions you have, and that you can search for the best one. What have you perceived so far? And that's the learning part that we're going to take care of in the third week. And is there any prior knowledge that we know about the process, about the problem itself, about the agent itself, and so forth? So it's very important that we don't think that intelligent agents can be omniscient, that they know everything, because this is not necessary for them. They are agents as we are, with the limited knowledge they operate in. It's just that based on the limited knowledge we have, we try to work as intelligent as possible and achieve the goals as well as possible. And that also means that we will never reach perfection. This is not what you would expect an agent to work on, but you need to look into some kind of goals that this agent can achieve. And this quality of what an agent can do, so how rational is an agent, also depends on the problem it works on and on the environment it operates in. So there is it's always very important if you build such an intelligent system that you really understand in what kind of environment, in what kind of task is your agent going to operate. So these are the things that you need to specify in your task environment for your intelligent agent. You need to tell it what it is supposed to do, where it does it, the environment, how it does it, and what it perceives. And that's the PEAS acronym, that if you get a certain task, you should be able to analyze it and tell me what kind of environment it does, what does it do, how does it do it, what does it need to measure, and so forth. But you have all the information here as well, because we have now here an example for the environment or the thoughts or the description that you would give for an intelligent agent in its operation according to these criteria. So suppose you want to have a fully automatic taxi that brings a driver from A to B, Schiphol to my home, and then we have to think up front on what is it we are going to build. And basically, what are the things that you need to do? And that is, first of all, the functional requirement to get me from A to B. But then it also needs to be safe. It should also be profitable. So you don't want something that's extremely expensive but doesn't work. It should be legal. So loads of criteria of what do I need to achieve in order to make it work in the first place. But then I also need to understand very well what is the environment to operate in. And for such a car, it's obviously the streets it is dependent on the weather, it depends on other pedestrians and so forth. What can you do? What sort of actuators do you have? You have a steering wheel, you have brakes, you have a horn, you have speakers and displays. And if you want to build an intelligent car, then you also have nowadays sonar, video, speedometer, engines, whatever, and GPS and so forth. And this is very important that you study these randvoorwaarden, as the Dutch would probably call it, or the properties of your task in which the agent operates in, that you understand and analyze that very well. And then there are different criteria according to which you can analyze these environments, some types. And I've used some of those words already, and it's good to set them up in a more systematic way now. So the one is the observability. So do you know, in an environment, all the aspects that are relevant to your specific choice of action? And if you look at a game such as chess, then it's a perfectly observable game. You know all the states. You know the figures, where they are. You know exactly what happens according to your actions. And that's different to Schnapsen. So I used actually this difference in environment types quite a lot to motivate what we are doing. So if you look at the 3-4 different scenarios, then you might have a solitaire game, a backgammon game, internet shopping. You want to find the best product as possible, as cheap as possible, or you want to have a self-driving car or taxi. Then solitaire and backgammon are fully observable. You know exactly where all the figures are, where all the cards are, what the value of the cards are, what the possible transitions are, and so forth. In internet shopping, you don't really know. You might have missed out on a website that you haven't found yet, and so forth. And in a taxi, it's the same. So you can observe part of the environment. You're not completely blind, but there's a lot of information that might be relevant that you don't have. Yeah?
I don't understand the difference between solitaire being fully observable and Schnapsen being not fully observable. What's the difference in those games? Because you still have a deck of cards in solitaire, right?
Good question. I don't have an answer. I would have thought that I was thinking of variants of solitaire where all the cards are known, but there might probably also be variants where you still draw cards. The one I have in mind that I've talked about a couple of weeks ago, I think all the cards were known, and you still had to do all the shuffling. But I might be wrong here. So
observable is about like seeing all the cards in this example.
yes,
Okay.
that would be the difference. So you see all the stones in backgammon, and you see all the cards. And as soon as there is some uncertainty about what could be the possible cards your opponent has in his hand, then that's the difference. The difference between deterministic and stochastic is that once we make a move, it's completely determined what's going to happen. So if I play a card in Schnapsen, the game engine has only one choice of giving me things back. So the game engine does not make any arbitrary choices. So in the beginning of the game, there is some element of stochastic. So the cards are mixed, and so that's the element of choice. But from the moment that the game starts, there is no element of choice anymore, a chance anymore, as I said before. So I play a card, and it's determined before I play the card, which is the card that I get from the stock. And the rules are clear. So if the same strategy is applied twice, the same cards, the result will be the same. So in backgammon, this is different, because in the game, it might happen that I play that I throw the dices, and I don't know upfront which will be the result of the dices, the throw of the dice. Yeah? That's a very important one, and that's the distinction between a static and a dynamic environment. So we hope, at least, that when we start a game of Schnapsen, that the cards won't change colors, or that my opponent will be the same after some move, and so forth. So the assumption that the situation in which I operate, the state I'm in, I do some choice, and then I get to a new situation, and the question is, does it still the same rules apply, and so forth. So in a way, there is a small, maybe little element of dynamic in the Schnapsen game, and that is when you move from phase 1 to phase 2, because there the rules change. Is that the point you wanted to make?
Yes.
Okay, great point. So in a way, solitaire, nothing changes, backgammon, nothing changes, but in a taxi, you have no idea whether some other agent comes in or a bicycle comes in from the side. There is nothing clear about the environment in principle. And that is obviously something that you need to take into account when you build your intelligent agent, because this makes it obviously incredibly difficult to maneuver in. I skip over the discrete one and just move to the single versus multiplayer one, because that's an important distinction that we have already seen, of course, with our Schnapsen game, where we have in principle, we would know how to do the game, unless, of course, our partner, our opponent, has also some interest and applies a different strategy. And the more of those agents who have their own interests you have, the more complicated your scenario becomes. And for a car driving in the city of Amsterdam, there is an enormous amount of individual agents doing their own stuff that you need to take care of. So that would be my summary for Schnapsen. It's not fully observable because you don't know the cards in the stock. It is deterministic and it's static, apart from maybe the moment where the phase 1 to phase 2 move happens, and it's obviously not single agent, but a 2-agent player game. Yeah?
So, static versus dynamic is about changing while the agent is choosing or changing before or after. Because in absence, the stage is only changing before or after you play, right? So
yeah.
when you make the decision, the state of the game is always the same.
Yeah, so that's why I also hesitated a little bit about this point, whether it really is a dynamic environment. You would call it a dynamic environment. I must admit, I'm not sure. So the question was whether at the moment whether the players take the decisions, they know in principle where they are, and it's not really during the moves that something changes. Yeah, yeah.
About the discrete part, should I, for every game actually, for the situation, do I have to make it discrete to be able to apply an agent to it? Like actually, the situation must be discrete for an agent to apply algorithms.
No, I think the kind of search algorithms that we apply now for our games, I wouldn't know how to do this if you didn't have discrete search problem.
The situation of the taxi that is, we say it's not discrete, but I need to make it discrete in order to apply rules to it. Let's take action.
Yeah, but if you don't apply a rule-based algorithm, but if you apply some algebraic algorithm on it, you might still be able to do something intelligent on it. So the point being, for example, if we have a simple game where you think of an what is it, the rational number. So it's a non-discrete problem, but I still can find a bigger one if I know some mathematics, or I can calculate with it and solve it in that way. So there are methods to play around or to deal with problems that are not discrete. They're just not the search algorithms as we would use them here in the first week of this. And also, of course, if you want to build a self-driving car, don't only build it on search tree algorithms. So I think that you also need a lot of sort of abstraction, and all these abstractions would then turn this into maybe some kind of discrete decision making. But the problem side, that is a typical problem for real AI problems, images and so forth. Okay. So the important point to mention, to memorize here, or to remind us of, is that building an AI system is, in some very controlled cases, such as games, is in a way relatively easy and restricted. So we can do a 4 weeks project of Schnapsen because the rules are clear, because the environment is pretty clear, because it's not dynamic and so forth. But real intelligent agents, like a self-driving car, they have to make the same kind of decisions, maybe like we do in the game, but they have to make them in incredibly complicated environments. So the decision of turning right with my car or turning left with my car is a very simple problem, left, right, and maybe you give it an angle or so. So the problem itself is not so much difficult, but the information you have, the sensoric information you have to deal with, the complexity, the problem is so much bigger, and you need to study the environment incredibly well. So it's far more complicated to have a real-world car rather than a car on a motor drive where you know that no car is coming my way. So it's, understanding the environment is really crucial for building intelligent systems. That's the only point I think that's really important here. And it's always a balance from the most simple environments, the simple problems, that allows us to do something smart in this course and to learn the methods, and even build an intelligent Go program that beats the world champion. But in many, many real-world problems, there's so much more that we need to take care of with our intelligent systems. One last thing about the agent is that obviously we also have a hierarchy kind of behavior of agents. And the first one is the one where I was talking about the heating agent, which just sort of measures the temperature, and if it gets the temperature and it gets below a certain threshold, then it increases the heating. Okay, so there is some sensor coming in, and it's a simple rule that says, okay, there's a condition action rule, as it's usually called. You get some sensor information, and the actuator is, okay, raise the heating. And that is already can be a relatively intelligent system, and there is a lot of things to how do you write down those rules, and there's knowledge input from humans and so forth. But obviously, often, and here's the pseudocode in the slide, so look at it, it's nothing spectacular. If we don't know all the things in the world, we might want to interact somehow with the world. And in order to do that, we need somehow to understand the world. We need to have an internal model of the world. So some kind of mental model is a very important notion in AI. So you really need to have a state of the brain, kind of the agent model. And there is a lot of research on this modeling as well. The next one is which goes closer to our rationality model. So the pure reflex agent simply does something on the basis of perception. But there is, as we said, the rationality really says that we should try some strategies in order to maximize our performance with respect to certain goal. And that means that we need some kind of goal-directed, goal-based agents that are aware of the state of the environment and also try to maximize their actions according to this goal. And this is probably the first type of agents that I would really describe as rational or intelligent agents. And then the next step is that you learn also from perception from the real world or from other agents, or particularly from yourself. And so this is the most advanced agent type, and we're looking at the methods for that in the last week. So let me spend 1 minute on this, and that is I talked about a lot about intelligent systems as the engineering aspects in a sort of exaggerated way of looking at things. So the engineering of AI agents, rational agents, we're building rational agents. But that's only part of the story of what I think we should do in this course. And we should do as AI researchers and experts, and I think all of us should somehow become partially that, even if you do information sciences or computer science. The point is that it should be more than just building a Schnapsen agent. That's already, I think, quite cool if you manage to write an algorithm that beats you in Schnapsen. I think that's quite cool already. But I think it's even more important for us that we understand why these intelligent agents behave a certain way. And that's the notion of the research that I've spent most of my life with, that developing methods and then doing experiments to show that things work, or at least to come up with the hypothesis of, as I said yesterday, determining the depth of an algorithm, of a search algorithm, with respect to its runtime and its performance, and what is the impact of doing the one on the other, and what makes the system intelligent, and what is the relation to the environment. So even with very simple problems and simple methods like the Schnapsen and the min-max algorithms that we apply, there are a lot of interesting conceptual questions that we should do research on, and that's also the purpose of this course, is more on this AI research. And that's why also the research project that you do and the report that you write, this is what you're scored on most in order to get the final grade. Okay, tomorrow there is practical sessions, there's working sessions, and I see you again next Monday. I don't know where, but anywhere somewhere. You see it in the schedule. Have a good weekend, everybody.
Clarification questions. When we talk about observability and partial observability,
Yep.
when we talk about partial observability, so we're saying can I see all the